by adopting this quirky title, we might confuse a few members of the public who were otherwise on their way to the allotment into thinking this was going to be a talk about gardening. Well, it is actually true that we're going to spend most of the morning underground. Visiting a monument and its garden, another proper activity for a Saturday morning. Our interest is attracted at a number of different levels. The site in its setting can offer feelings of consolation and beauty. Its official history gives it a public face. But upstairs and downstairs and under the ground lurk the private stories that give it humanity. And these stories, in turn, join the bigger quest, the when and the how and the why. Encountering a monument for the first time is comparable to meeting a new fellow human being. Meeting somebody new, we begin with the clothes, the outer form, the face, the voice. Then, if you're a doctor, do various tests to get under the skin, to the flesh, the bones, the chemical mix, to find some trends in the incredible complexity. In a person, there are thus certain aspects, like the face, that are unique, hard to define precisely, and yet unmistakable to another human. And there are others, like blood group, that could be scientifically classified. Deposits, archaeological deposits, are at least as complicated and are also, like a human body, multi-conceptual. At one level we use our scientific toolkit, at another our human intuition. Archaeological investigation aims to write the history of sites and landscapes with a view to enlarging, enriching and understanding better the human experience of life on Earth. And I intimated last night my conviction that our ability to do this depends not on chance encounters, but on what we want to know, what is left under the ground, and also the society we work in. Now, my subject now, this morning, is what's left underground and how we can see it or sense it. And my aim is to persuade you that archaeological strata don't lie supine, awaiting rediscovery. What we see depends on the measures we take to see it. What we see is what we seek. Thus, our question about the big underground is not so much what is there, but what can be defined by us today, and how. We know that this underground world is startlingly different everywhere we go. Buried under dunes and caves, in swamps, underwater, on chalk, clay, in tells, in steaming jungles, and deep frozen under permafrost. She'll visit sites of this kind today and tomorrow. It's also startlingly complex. Reaching down and grabbing a handful of garden soil, Richard Dawkins famously announced, there are 4 times as many microorganisms in this handful of earth than there are people on the planet. Well, soil is only one kind of archaeological deposit and not the most important for us. We know what it was for, i.e. to grow crops. And although there are a few things more satisfying for gardeners and farmers, not even they would claim that all human life is there. For this reason, as we'll see, the methods of soil science won't map onto the needs of archaeology. What we need to define varies in scale from the very big to the very small, from the monument to the micro, the mega to the nano. And our ability to make these definitions is getting better and better. 60 years ago, archaeologists began routinely to collect the bones of animals as well as humans. 50 years ago, Sebastian Payne was urging excavators to use sieves to find smaller mammals, birds and fish. 40 years ago, Stuart Struve was extracting plant remains at the Costa site by flotation. 30 years ago, Harry Kenwood was showing what could be done with insects. 20 years ago, Richard Evershed was extracting lipids from the walls of pots. 10 years ago, we were learning how to interpret isotope signatures trapped in teeth. 5 years ago, DNA was isolated in bones. 2 years ago, in the soil. And last year, the proteins of particular animals were being recognized in the ground. So my table here sums it up. Note that in archaeology, nothing stops being interesting. So the shopping list gets potentially longer every time at every site. I say potentially because although the toolkit is bigger, not everything can be applied everywhere. It all depends on the terrain. Well, going from big to small, I think gives us a convenient way, as convenient as any, to structure the agenda. So we'll start big and then go smaller. In most countries, the archaeological units of interest are landscapes and the site, both of which have an academic as well as a social as well as a legal meaning. In practice, these represent packages of potential information, and we're led to them through survey, or sometimes chance, or sometimes hunch. While a castle is fairly easy to recognise, other kinds of sites and landscapes are more exotic, and we may not be able to guess where the edges are or give them a name. Well, let's strip the top off some of these sites and see what we see. There's an immediate difference in character as between well-stratified and unstratified sites, which in turn prompts a difference in approach, and in fact a whole difference in philosophy. In very general terms, well-stratified sites prompt a macro response, i.e. response to the stratigraphic riches that are evident. However, where strata are invisible or hard to define, obstinate excavators have been driven to make more of them, and the result has been progress in micro and nano definition. Actually, of course, most sites are neither fully stratified or hopelessly unstratified, so there will be considerable crossovers between them. Excavators need to be as versatile as their sites are varied. And what I'd like to do in this talk is to enlarge the toolbox, put more options in the hands of project designers, and cast a little doubt on standard procedures applied invariably to town or to country or to both. Macro distinctions, i.e. those visible to the naked eye. This picture was just meant to give you a kind of contrast between the flat and the deep. York Minster on the right, Sutton on the left. So these macro distinctions, those visible to the naked eye, depend on deposits of different colours and textures and the interfaces between them. If you look at a section, these distinctions can be seen and defined and recorded as entities. This process turns a pile of earth and stones into structures, activities, episodes, and events. Here's a 3D image of such a sequence divided into its stratigraphic bits, context, features, and structures. Now, we already noted two things about this process. First, that the existence of these stratigraphic units depends on an act of definition. Looking at a section or a surface, different people will see different numbers of interfaces depending on what they know how to recognise. Furthermore, the number you see depends on how hard you look. If you clean very carefully and enhance with a light spray, you will see more layers than if you sharpened it up with a shovel. One way of monitoring this, as I suggested yesterday, is by using the idea of recovery levels, which does at least remember in a well-ordered way what tools were used and what measures were taken. Conversely, how hard you look should determine how carefully you record. No sense in sieving a pit full of bricks or drawing in colour a concrete drain unearthed by a bulldozer. Later, we will see how recovery levels serve the design of projects in deciding what must be done and what it will cost. For the moment, let's just agree that a context needs a recovery level, otherwise it can't be compared with other contexts. In other words, we can only compare assemblages excavated with the same degree of attention. If one pit is excavated with a trowel and sieved and another with a shovel, their bone assemblages will not be comparable. We can also note at this point that variation in the legibility of strata is already built into the resource as a whole. Town sites are in general well stratified, but not to the same degree. In some places, strata accumulates, in others, it dissipates down slopes. In some places, organic material is well preserved, in others it isn't. Hypothetically, we can award points to sites depending on how well preserved is the assemblage and how legible the strata are. In the picture on the left, a good site follows the arrows, but of course it is a natural tendency of the curious to look harder when they see less. Therefore, recording strata is not just a matter of observation. We put in our own variables as we work. Similar factors of variation affect the most crucial of all the procedures applied to a well-stratified site, putting the stratigraphic units in order. A section has the weakness of reporting only a very local sequence, but it has the strength of providing a full record of what the sequence was based on. Those who favour the Schnitt method also emphasise its checkability and feel they are making more objective reports of the stratification than they would if they ordered each context one at a time. Stratigraphy composed of single context records of the type otherwise known as the Harris matrix, as I mentioned yesterday, has created a fervent following, and the method is an excellent one. It asks you to define the context and place them on a diagram which shows the order in which they were deposited. The result is an account of the stratigraphic order which includes everything that happened on the site. There's no doubt that this is quintessentially useful, if not inevitable, method for ordering context in well-stratified sites. My own published comments about it, widely misreported or misunderstood. Not that it is wrong, I never said that, but there are ways of developing the same basic idea which have their uses too. I also think it needs to be acknowledged that you can't make much use of a stratification diagram when there isn't much stratification. So that to demand the adoption of single context recording everywhere would be absurd. My theme in these lectures is that there is no method that must be adopted everywhere. Methods serve people and not the other way round. You will note that in this example on the screen, the contexts have been grouped together where they were interpreted as forming part of the same episode. Excavators always notice this sort of thing, and just recently have been inclined to bring back this additional level of interpretation into their site records. This seems pretty sensible to me, and I think it's helpful to formalise it. One way of conceptualising the family of stratigraphic units, which I've long championed myself, is as a series of sets. If a grain of sand is the smallest thing we can see with the naked eye, we can call it a component. A set of components, via an act of definition, forms a context. A set of contexts forms a feature. Each level of definition requires a high level of interpretation. None of them, neither the component, the context, the feature, or the structure, exists in the sense that it was tested for scientifically. Our macro units are all defined by humans using a kind of measure of consensus. We would all probably agree we can see sand. most will be prepared to sign up to the contexts. Those who have seen the kind of associated pit stones and shadows before will be happy to sign it off as a post pit. Some will want to go further and say it supported a post 6 feet high. Others will feel sure it was a replacement, and so forth. This is all in the nature of our art or science. If you think the interpretation has flown up out of sight, you can always return to the last interpretation that commanded a reasonable consensus. In this way, we create a kind of vocabulary for our subject, which works locally and which works further afield if humans behaved in a similar way there. If a set of context makes a feature, and a set of the feature then makes a structure, it may not, but the fact that it sometimes does gives us the impetus to look for one. Needless to say, once one can accept that strata can be defined in a conceptual hierarchy like this, it is not too daring to allow these higher order concepts a say in the model sequence that is a strat diagram. And they're beginning to pop up here and there as excavators strive to answer the question, what happened here, in a nice, succinct way. Here's a group matrix from Tom Saunders with the context gathered into groups. And here's his land use diagram, so-called, with the groups shown succeeding each other in space and time. Here's Colin Renfrew's sequence diagram from Phylocope. And here's my old 1974 strat diagram for Durham Sadler Street, with context gathered into features and features into structures. And here's a little analysis carried out many years ago by Malcolm Cooper, showing that the Harris matrix and the multi-concept strat diagram were just different ways of representing the same thing, i.e. the sequence of stratigraphic units as defined by their excavators. Now, one area where a difference of opinion endures is the question of whether higher order concepts ought to be defined on site or only later, as espoused by Steve Roskams in his book Excavation. The variants of the Harris matrix introduced in recent years, i.e. by Bruce Watson at MOLAS, by Magnard Dallen, Norman Hammond, Richard Pace and so on, all tend to prefer to record in single contexts and bunch them together in the post-excavation phase. Now, it makes sense to me to do this higher level interpretation on site while you can still see the stuff, and to formalize it in feature and structure records on site, rather than just give an opinion on a video, for example. But I have to admit there's an important financial issue here, which we must come back to. There is a time penalty, and therefore a cost penalty, in defining and interpreting features on site. And this is not the first time that we'll come up against the big problem of archaeology, particularly in America and Europe, which is that if you want to do things so that they mean more, they will also cost more. Well, the story so far is that stratified sites can be ordered in exquisite detail, and that we could go further still by enlarging the concepts and grouping them into families. Meanwhile, we're still faced with the fact that unstratified sites, i.e. sites with no strata or no strata that's visible, represent by far the majority in all countries where people dig. I don't want to labour the matter, but it is obvious that in flat sites we need to take special measures to bring anomalies into focus and define them as contexts. In temperate climes, this almost invariably means working in a broad area, having a tower and plentiful supply of water on site. We also need special measures to put the human activities into order. Stratification can play a part here when we have it, but happily there are many other devices for ordering. For example, alignment, which reasons that, say, graves near to each other in time could have similar orientation. Assemblage, where the order in which graves is dug is implied by the order in which grave goods were manufactured. And the content of the backfill. In the famous examples quoted here from Yevering, a timber hall had burnt down, and Brown, Hope, Taylor separated the graves into three groups. Those with no charcoal were dug before the hall burnt down. Those with fresh bits of charcoal were dug straight after the fire, and those with weathered pellets of charcoal were dug sometime later. Pretty neat. Now, my job here is not to go into all these methods and many others in detail. It's just to emphasize that every site is different, and our approach to defining stratigraphic events and putting them in order should be creative and ingenious, not passive and routine. The task of the field archaeologist is to do what works, what is appropriate, and not to do what they always do. Now I want to slide down a few gears from the macro to the micro, under which heading I include properties that can be targeted, detected, and read on site. But note that they do not necessarily refer to things that are visible. First, it could be useful here to introduce the idea of the proxy, now very favourite word in archaeological writing, whereby archaeologists detect an activity from objects or features which are not direct evidence for the activity, but imply it or stand proxy for it. A straightforward example was provided by Cecily Spall's detection of vellum working at Port Mahommed. She didn't find any vellum or parchment, but she excavated a workshop area with a building, a yard and a tank. There was a curved knife, such as is used in trimming parchment, pumice, rubbing stones for smoothing its surface, much ash, containing spirovis shells showing that seaweed had been burnt, producing a strongly alkaline compound suitable for toying and pouncing, trimmed cattle metapodials and small round pebbles, and these are paralleled in the stretcher-pegged frames of modern parchment makers who use small pebbles to wrap the corners of the hides around to prevent them from fraying. The connections here are all inferential, that's to say, the individual pieces of data converge on a single likely activity, here the making of parchment, without actually, in this case, having any of the product. Most micro and nano interpretations rely on the proxy idea, and as we'll see, they flourish. Among the earliest advances were among paleoecologists who enriched the assemblages with fragments of plants and insects. At first, these were used in a kind of adjectival way, sheep lice, implying sheep, for example. But Alan Hall and Harry Kenwood realized that the species they identified were signals of something else, in other words, proxies. Dead insects, for example, were proxies for whatever they fed on. The furniture beetle implies furniture. Then they were shown to represent a micro-environment, the dead insects belonging to outdoor versus indoor groups. It wasn't only insects that were forming up as silent witnesses to a situation or activity. Fragments of plants and animals were also signs, and when found with artifacts, they seemed to form repeating sets. Harry and Alan called these indicator groups, which pointed to certain crafts, and the ones that they were particularly interested in were crafts associated with wool. Others have taken the idea of the indicator package forward. It has had great success in the Levant, especially in the hands of Alistair Northedge and Wendy Matthews at Telbrach and Chattelhoyk, using what they term micro-stratigraphy. In reality, these are micro-assemblages. So beetles associated with camel dung inside houses imply a hearth burning camel dung rather than a camel squatting in the front room. It's an interpretation. Now we're going smaller still into the molecular world, the nano world. So some versions of this kind of what you might call CSI archaeology were already underway at Birmingham, for example, concerned with the human body, the so-called forensic archaeology, named after the legal profession in which it has its most common application. But what we're doing now, I think, is a lot broader than this. CSI archaeology is looking more specifically at what happened and more widely than just the analysis of human remains. Now, this field, which I'm terming nano-archaeology, has taken off with tremendous success in the past few years and points a powerful finger at the future, I think. We're dealing here not with made-up entities like contexts and features, or with sets of microscopic debris discarded in situ. Nano-archaeology operates at a molecular or an atomic scale. The elements or molecules that it finds have been adsorbed into the deposit from something that was once there. Occasionally that something can be inferred directly. More often what we find is a proxy for some other material which is now decayed and disappeared. Here is one of these first of these kind of crime scene investigations, the atomic mapping of the robbed-out burial chamber under Mound 2 at Sutton Hoo in 1988. Previous excavations in this mound, 3 of them, had left us with only a few scraps of artifacts, including a number of ship rivets. Effectively, the horse had bolted, but that never worried Sherlock Holmes, and it didn't worry us. We planned and photographed the chamber floor, which showed a few swirling anomalies, and then swept it with a metal detector, noting the location of ferrous and non-ferrous signals. Then we took 640 30-gram samples from the floor and had them analysed by an inductively coupled plasma spectrometer, which simply notes the amounts of each element present. So this reported the amounts of the guessed elements, if I can call them that, i.e. the elements that are not sand, they're not silica, they're not oxygen. The main response was given by phosphorus and various cations, iron, copper, barium, calcium. There it is. Iron and copper mapped onto forms of anomaly likely to be artifacts. Circular patch of copper has a good chance of being a bronze cauldron, and the swirly iron thing a good chance of having been where a chain lay. We're making these analogies with Mound 1, of course. Another set of elements clustered together at one end, aluminium, strontium, phosphorus and barium. And we knew from experiments with graves, particularly the sandmen, so-called, elsewhere at Sutton Hoo, graves which didn't have skeletons but had sandy forms of bodies. We knew that these elements were proxies for the human body. Well, others have carried this kind of chemical mapping out of the grave and into the settlement. Here's a chemical plot inside houses at Chattelhoy. The calcium-enriched areas, which on the top one, the calcium ones imply where a plaster floor was, and the potassium-enriched areas imply ash from hearths. Plots that use cations alone, i.e. metal atoms, have their uses at their perils. Papers published in Journal of Archaeological Science last year show both optimism and pessimism. Sayano and Scalengi say that archaeological occupation layers can be detected by signature groups of lanthanides, even when mixed in to a later soil. But Donald Davison at Stirling and his colleagues express caution, I think quite rightly really. Some elements do seem to be reliable proxies for human habitation, but others, such as titanium, vanadium, aluminium and zirconium, showed in his experiments virtually no correlation with the archaeological remains on the abandoned farms they tested. The variations in their concentrations, that's those elements' concentrations, were thought to reflect geological differences. So you think you've got a signature group, but then you try and transfer it to another site, because you're transferring it to new terrain, new geology, then you might get a different answer. Well, Dawson and Co. back certain elements as being good indicators of human activity. Barium, calcium, copper, phosphorus, lead, strontium and zinc, for example. For Unken's slump, the telltale elements were copper, chromium, tin and neodymium, while depletions of iron and magnesium were also found to be universal indicators of human occupation in the house plans. Now, you might think that this is all too vague to entrust oneself for a ride. I just think it's a ride worth going on, and one that promises new vistas. When you think of the tiny number of examples that have so far been used in this discussion between scientific experts in the Journal of Archaeological Science, I mean, there's an awful lot still to do. We just let's forget, you know, the 50, 100 years of empiricism which allowed us to interpret many things that are not controversial today, such as post holes and so on. Perhaps the most convincing project of physico-chemical mapping I've yet seen is the Athel House, excavated at Reykjavik in Iceland and studied for her Cambridge PhD by Karen Millick, who is now at Aberdeen. And she won't thank me for this picture, it was the best I could do under the circumstances. The problem with this kind of building, as many Scottish excavators will know, is that while they are at once large and imposing, by the time we get to them, there appears to be nothing there. Turf is among the implied building materials. This is a Viking house, of course. Turf is among the implied building materials, and this ought to leave iron-enriched microstrata. Other kinds of decay products should be present too. In fact, as Millett says, minute residues, minute molecular residues, have actually a much better chance of remaining in situ than bones or artifacts which get dispersed by animals and humans. So, drawing on earlier ideas from Helen Smith and others, Karen applied a number of remote sensing techniques to the excavated floor surfaces. These were micromorphology, ICP mapping, that's the mapping which shows the cation distribution, acidity, testing for organic matter with loss on ignition, magnetic susceptibility, hence the word MAXUS, electrical conductivity. Now, these report different physical and chemical properties which imply different materials, which in turn imply activities. In other words, a kind of proxy chain leads back from what has stayed in the soil to what was mostly done in different parts of the house. Here are some of the chemical plots. Here. And here is the overall interpretation. And very cosy it looks, I think you'll agree. The proxy chain for each of these activities identified is quite involved. So I'll just serve up a couple of samples and hope it meets with more approval than scepticism. In the southeast corner we have sodium and magnesium enrichment, suggesting seawater, seaweed or urine, plus high electrical conductivity. Overall, this is read as a place where wool was washed and degreased. Along the east aisle we have articulated phytoliths in dark greyish brown organic silts, implying compacted grass. There's zinc, barium, strontium, copper and nickel, suggesting organic matter, unburnt bone, fragments of pumice, jasper, etc., either side of a sitting space. Interpretation, a grass bed, sat on to chew bones and work stone. Now, this is a 400-page PhD and that many other examples. It's not a shot in the dark, a wouldn't it be nice type of project. The approach is perhaps more significant than the results. It treats the house like a complex organism, not just to be sliced or dissected into contexts, but to be examined with a battery of sensors, to be interrogated for its memories. MagSus was among the methods deployed by Karen-Millek. We're used to seeing it trundling along the surface to produce geophysical surveys, but magnetic methods are also used to resolve questions about strata we can't see. Andy Harris is by way of being a magnetic champion and has had terrific success applying magnetic methods in cave sites. Here are 4 of them deployed at Pinnacle Point in South Africa. They're numbered here, so I'll just tell you what each one is supposed to demonstrate. Number 1, it examines where odd stones could or couldn't be a hearth. If they're a hearth, then they'll have all heated up together and therefore all preserve the same magnetic alignment. So that's how you can tell. Number 2, among the mass of opaque strata, MagSus can distinguish hearths, but also archaeological strata of the Middle Stone Age, that's where it says MSA there, and distinguish that from colluvium. So although it all looks much the same, the MagSus is reading where there's a change from a colluvial layer that's come in, or a occupation layer that's formed in situ. Analysis number 3 is done on ochre, which is the Paleolithic colour of choice. It's highly magnetic, and its magnetic properties differ from source to source. Number 4, the MagSus readings of layers vary with rainfall and can be aligned with oxygen isotope periods to give an approximate date. So it's not magic, it's just an application or a variety of applications which reflect on different properties. Occupation can be mapped from traces just using MagSus. The ochre can also be provenance, since different sources of the mineral give different magnetic readings. So we're making some very interesting progress there. In a 2009 paper, Hilstrow and Isaacson extended the range of detectables to include lipids, i.e. the insoluble decay products of organic compounds. They plotted organic traces on the floor of a reconstructed house at Lyra in Denmark, noting areas enriched with copperostanol and 24-ethyl copperostanol. These are compounds that can be directly associated with what they call fecal biomarkers for herbivores, which in ordinary person speak are cowpats. Organic molecules, the stuff of life and their proxies, are very much the targets lining the new frontier. Don Brothwell's ERC project aims to develop skills in detecting residues in human burials, both from the body itself, stuff that it ingested, and materials applied to the body, i.e. embalming. And he's using the whole box of tricks: scanning electron microscopes, EDX, microprobe, chromatography, and so on, to report decay products at the macro, micro, and nano level. And what he's after are resins, spices, waxes, gums, bitumen, fats, and oils. These can all be deduced from what you actually get, which are terpenoids, alkanes, hopanes, sterols, etc., each with its diagnostic molecular structure. So they're just mapping the residual molecules and inferring what must have caused them. A pilot study on 2 Yemen cliff burials claims to have detected proxies for skin, hair, uric acid, and cholesterol. Now, you may say, well, that's not amazing, because most people have those things. But probably it will be useful, at least to modern forensic medicine. For example, it can detect whether a dead person was using drugs, but can detect that, decades after they died. In 2009, the Journal of Archaeological Science reported the extraction of alkaloids of the mind-altering banisteriopsis. I would have thought your mind would have to be quite active to be able to say that on Saturday morning. From mummies in the Azapa Valley, this area is already known for its graves, which contain tubes and what they call snuffing tablets, which presumably are for snuffing something, your banisteriopsis. Animals usually leave lots of bone, but on some sites the bone is gone. There's never much there, or is otherwise barely detectable. There's Don Brothwell, by the way, in characteristic mode, surrounded by skulls. That's how he likes to be. There he is. Don is well past retirement age, but has just embarked on this new project, so there's plenty to come from him. ZOOMS is a zoology mass spectrometer group directed by Matthew Collins, which aims to distinguish the collagen of different animals from minuscule samples. This is pretty recent work. Collagen is a protein, consists of 3,000 amino acids, which together provide a signature of the animal species. Collagen is protected underground by being bound in fibrils and trapped in the lattice of the bone, apatite. So far, it's been tracked back to a survival of 1.5 million years. Unfortunately, it melts at 36 degrees centigrade and is eroded in hot, and especially in hot and wet soils. The collagen chain consists of repeating subchains of peptides of standard length, and the weight of each peptide depends on the amino acids present in it. So the peptide has a mass typical of its bunch of amino acids, and thus of the animal species. Quite neat, quite simple. So you put the crumbs in water that are supposed to have animal bone. You cut the protein into its peptides chemically, use mass spectrometry to identify which peptides are present. Different animals have different peptides, so we can tell a camel from a rabbit. Well, I know you've got a real one, it's easy, but we're talking about tiny things here. And in theory, every animal has its own special signature. It may interest bone people here to know that zooms can at last tell a sheep from a goat. But not if they've got the bones, only if they've got this tiny piece of chemical, which they can get from the bones, of course. This analysis is becoming affordable. Okay, it costs £6,000, but £6,000 can do 100 individuals. So you have to sort of set it up and run a whole lot through, and then it can be done. Well, this new branch of nano-archaeology is called Proteomics, or that's what they call it, since it focuses its energy on distinguishing proteins. Proteomics has been used to identify fish processing on 30 flint artifacts from an early Neolithic TRB site in South Sweden. And they demonstrated, they thought, a correlation between fish protein and use-wear analysis. Now, I need to mention two of the most exciting kinds of molecular labelling, isotope and DNA, but both leave us field archaeologists with a number of problems. I'm not going to go into them in any depth. Oh, sorry, that's the sheep from the goats, just to show it. Well, the isotope maps of strontium and oxygen are used to detect foreigners in cemeteries, since the isotope signatures vary with groundwater and get into the childhood teeth. Now, numerous examples of successful analyses from Warwickshire to Peru. Of course, these inquiries feed off human bones and teeth and require lots of samples to sustain a historical argument. So the method does not itself influence the amount of destructive excavation that's done, except perhaps to increase it. So this is something we need to bear in mind, because what we want of our scientific techniques is not only they tell us more about a particular site, but they can also tell us more about a particular site without having to excavate more of it. DNA is the other wonder analysis for human and animal remains. It still works best on modern samples. Here's a plot of DNA extracted from 3,000 modern Europeans, offering a clear correlation between DNA and birthplace. However, ancient DNA, A-DNA, is really what we want because archaeologists don't want to make any assumptions about the way people may be related. That's what we want to find out. But A-DNA doesn't really survive in hot climates, and it is destroyed by most recovery and storage schemes. A-DNA samples are also notoriously susceptible to contamination. Modern DNA is picked up from the highly intrusive biosphere in which field archaeologists themselves work. Now, it's against this cautionary background that we should consider the triumphant investigation which is known as The Farm Beneath the Sand, which was published last year. From previous findings of plant and animal DNA in Siberia, North America and New Zealand, Martin Hebsiard and his colleagues argued that A-DNA in soil, or dirt DNA as it's now known, is less subject to degradation and leaching in cool conditions and quickly binds onto clays and sand and organomineral complexes. Thus, A-DNA in soil, dirt DNA, does survive and may not move very much. Their target site was a Norse settlement in Greenland, dated between 1000 and 1400 AD, which had been excavated in 1992 from beneath 1.5 meters of sand and gravel. The faunal and insect records had indicated that this farm had not been occupied continually through the period, although the fields around had been grazed. Thus, there was a control on the DNA experiment, and this DNA experiment took place in an adjacent field, so it was as though they didn't know the excavation had happened. A small trench was cut through layers of peat interleaved with sand in the field. It was about 50 meters from the excavated buildings, and samples taken from the section with a hollow pipe. 7 cores were sealed and frozen and taken to laboratories in Copenhagen and Murdoch, Australia, via Canada. The surface of the samples was spiked with a known DNA molecule so that they could later check whether this spiked molecule had interfered with the inside of the core. The DNA in the inner cores were then amplified using the PCR method and then sequenced. The sequence of bases then gave the most likely animal present and, in their argument, the quantities. Parallel cores were used to provide AMS, radiocarbon dates, from layers of peat. Well, the chief species present in the inner cores were cattle, sheep, goat, mouse, reindeer, and human. The humans were disregarded as being likely contaminant. You'll see in this that they dominate the latest 2 parts of the core. For the animals, both the species and the quantities were considered representative. It was found that sheep and cattle arrived together around 1040 AD, but while the sheep population remained steady, the cattle population fluctuated. High, low, high, low. Both species then became absent from 1520, which also reinforced that the method could be valid. So these results correlate well with the excavated sequence and its bone record and raise confidence that these samples tell a story without too much leaching or contamination. The project showed that DNA survival does not need permafrost but can remain representative in temperate and wet conditions. In other words, there's no reason why it should not work in Scotland. But of course the DNA reports a general presence from urine and faeces rather than the use of specific animals, which is what the bone record reports. It's a start. The sequence provided by the farm beneath the sand is in some ways thrilling, since it implies that the history of the world can be explored locality by a scientist with an auger. However, history is not just a general sequence, but many interwoven narratives, So DNA joins the toolbox, but mainly in the service of environmental change. So what has the future in store for us next? Will nano-digging join up with remote mapping so that as well as chemical and microchemical samples, we can talk about remote sensing as indicating properties of underground sites? If so, the rewards will be tremendous, because it means that we can look at sites and understand more about them without having to destroy them. So we don't have to be permanently confronting the conservation mission. We've already seen that MagSus is discovering properties in strata way beyond simply knowing it's there. We know that ground-penetrating radar also reports more than we can so far understand. It can also report it in time slices, i.e. the platform of anomalies encountered at different depths. So it's already trying to mimic the excavation process. Here's an aerial photograph of part of Roman Roxeter, and here, courtesy of Prince Gaffney, are some GPR time slices, providing images at increasing depth from right to left. Lawrence Conyers' 2010 article in Antiquity shows how radar can find the slope of the principal occupation surfaces while they're under the ground and remap the anomalies onto them, offering, or at least claiming to offer, the changing geography of a site, in this case a Nabatean garden in Petra, and you need to read this from right to left. Well, it's not perfect, but we can have little doubt that this is where the future's going. As we get to know the underground world better, the power of remote mapping and the power of nano-digging will operate a pincer movement on the old dig and look mentality. Our methods will be less butch, but our stories will be more interesting. Radar reads interfaces, especially in nice dry sites where the radiation doesn't get attenuated. What we've seen of our nano methods so far means taking readings directly underground. That is, we need to dig, sample, and then infer the invisible part of the assemblage. Could we ever get to the point where we can not only map underground without going there, like radar, but identify elements, molecules, materials, all the components of context, macro, micro, and nano, and do it from the surface? Here are two instruments already in use, which suggests that this idea is not quite so crazy and might even be just around the corner. The IR gun works by distinguishing different organic materials that return different reflections from IR light. The IR gun has been used in Sweden to find organics by simply pointing it at a section. I don't believe it. It recognises bone, textiles, and vitamin C from fruit. I was reminded that we had an amazing guy at Sutton who arrived, called Mr. Lovegrove. He arrived with an instrument which he called the hazonometer. It looked like a water pistol with a micrometer screw gauge attached to one end. And I said, "What's that do?" He said, "Anything. It discovers anything you've got." And he had an assistant. And the assistant said to me, "He's very, very sensitive. Be careful with him." He had this water pistol. He held it in his arms like that. He went into hazonometer mode, and I said, "What can you see?" He said, "So, hang on a second, I've got to look it up." And then he twiddled the micrometer screw down, and he had a big he had a big sheet, a bit like the prices of used cars. Yes, said, "There's gold here, there's silver, there's iron." He's looking at the mounds at this point. I said, "Oh, really? Is that so?" I said, "Is there any wood?" He said, "Hang on," set the micrometer screw down. And then he sort of traversed around like that until he was actually pointing at top hat wood. Then he went into, judder mode. And then he said, Sorry, there's nothing there at all. What about these trees? Oh, it's attached trees. And then she said to me, you know, you're displaying a lot of cynicism here. You're hurting his feelings. I said, really sorry. Anyway, this one, hasten to say, since it's a company that's labelled, it can easily sue, it seems to work. The XRF gun is much better known. Lots of people have used these, and they can determine the presence of copper and silver and so on in a possible workshop. It's being used, for example, by Kato, Nekai and Shinto at Raya Port. This is an 8th to 12th century Islamic glass factory, and glass vessels with low titanium and iron and high strontium, probably produced by a Syria-Palestine workshop in the 8th century, and samples with high levels of calcium, titanium and iron, probably produced in Egypt in the 9th century. So you see, you've got differences there, and you can use it on site, and you can start to explore the assemblages while you're still there. Now, it seems a little short of miraculous that these gadgets can read off the presence of specific atoms and complex molecules by just waving them above the surface, like reading a barcode. Will there be a time when they can operate remotely? To some extent, they already do, and that time will come more quickly, if we want it to. Like many other things in life, if you invest in something, if you believe that it could be the future, then it will happen. We waited a long time for geophysics, and it was really the Moors murders that advanced it. It wasn't archaeologists. We didn't show nearly enough interest. But if we show interest in this, we will get the investment we want. So should we? Well, I believe it is important to embrace this kind of technology and develop it for two quite urgent purposes. In the first place, in the service of evaluation. There has been a huge improvement seen over the past 30 years in predictive deposit mapping, but it still isn't good enough to put a clear value on an archaeological site in advance of its redevelopment, and most evaluation projects resort pretty quickly to test pits and trenches, quote, just to be sure. Part of this is having greater confidence in the instruments with an appreciation of what they can do, and to pass our own convictions on to our collaborating professions, developers, of course, in particular. It would be a rash planner now that withheld planning permission on the basis of a radar plot. But confidence could come if there were more remote sensing studies of sites, which were then published after excavation. If the predictive mapping also showed the old water mains, cellars and foundations with convincing clarity, there could be a better chance of using such plots to make decisions about building and about research opportunities at the same time, thus combining the two design imperatives. The second urgent purpose concerns sites that are not threatened, but not available for research either because of stringent conservation policies. Now, we'll need to come back to this in Lecture 6, but let's just observe here that remote mapping is no longer about finding sites, but about studying them. My very brief review of technology in the making, brought together from many different sources, shows that given sufficient ingenuity and R&D, even the most sacred places, like Stonehenge, could be studied in depth without irreversibly digging a hole in the middle of it. The journey we just undertook from mega to nano was intended also to broaden the concept of an archaeological deposit and to convince you that it deserves much more than the same single response each time. The context is not a unit of human activity. It's a macroscopic unit of strata defined by colour and texture. Occasionally, its interfaces are nice and clear. Mostly they aren't. Clear or not, the context represents only one set of macroscopic properties, and perhaps not the determinant one. Context-only recording is inadequate. Interpretation at the trowel's edge is only a tithe of the interpretations that are possible. They're necessary, but not sufficient. When we can, contexts need to be resolved into higher concept families, features, interpretive ideas that express human actions, paths, pits, floors, walls, graves, and so on, and the features form patterns too that show concepts of still higher cognition, a building, a ritual space, a kiln group. The context also needs to be deconstructed beyond its macroscopic components to reveal its microchemical and microbiological properties, because so much lies hidden there. These diagnostic properties do not necessarily map onto the context. You've only got to think of urinating cattle, which create an intrusive context of their own, spread untidily through a space. And yet this invisible context marks a bias. It can be seen that this multi-concept, multi-technique deconstruction of an archaeological deposit is taking archaeological investigation into the intellectual forum of the arts through the media of the sciences. Our inquiries will serve historical, processual, cognitive goals equally well. Archaeological investigation does not exist independently from what it wants to find out. But once mapped out in the design phase, it can proceed using its own logic. The new technology is thus rearming the objectives of archaeological research in ways that we've yet to fully appreciate. In some ways, research needs to catch up with what archaeological fieldwork can now do. If this transition continues, excavation could or should be transformed from a heavy shoveling exercise on a building site to something closer to a crime scene investigation with strong laboratory backing. We could see a transformation of the workforce from the donkey jacket to the white coat. There could be a transformation in the way archaeologists are regarded and the amount they're paid. In the commercial sector, this transformation is much needed, but I'm getting ahead of myself. These matters are not so much concerned with science per se as with the way archaeology is procured or purchased by society and what society wants us for. These are the things that make archaeology the career it is and influence the career it should be. And that's the subject of my next talk that happens at 2 o'clock this afternoon. Thank you.
Questions?